All right, so hello everyone. Welcome to episode 51 of Warsaw Quantum Computing Group Meetup. My name is Paweł. I'm one of the organizers, and we welcome participants from other countries like UK. And today we have pleasure to host our next great speaker, Marco Fellous-Asiani. So Marco is from the Center for New Technologies at the University of Warsaw here in Poland, and today he will tell us about minimizing the energy consumption for large-scale quantum computers. So this meeting is recorded, as you can see, so hopefully the video will be later available on our YouTube channel, as usually. If you have any questions, you can post your questions on our chat. Marco, would you like to have this meeting also more interactive so that the participants could interrupt? Okay, so you can also, or we can try to ask questions, try to interrupt and ask questions during the lecture. We have Maxim from Spain, which is great. So before we start, we would like to thank our strategic partners for supporting us, Cogit, Snarto, and Sonovero R&D. We also thank our honorary partners for helping us organize this event. And that's all from my side, so I hope you will enjoy this talk. I will now stop sharing my slides. Marco, if you're ready, you can share your screen and the Zoom is yours. So thanks once again for accepting our invitation. I can see your screen, you can see your slides, so we can start.
Okay. Thank you for the invitation. So what I will talk today is indeed approach to minimize the energy consumption of large-scale quantum computer. And so this is a work mostly based on this preprint on that link. Actually, the preprint has a different name. It's called Optimizing Resource Efficiency for Scalable Full-Stack Quantum Computer, but it's what I will talk about here. And there is also a preliminary work published in PRX Quantum that is preliminary study to what I will present. And so I work at the Center of New Technology at the University of Warsaw. So the first thing to understand this problem is to understand the connection between quantum computational and quantum energy advantage, because the two are in some sense related. If you are not fully familiar with why we need quantum computer, this is a bit of a reminder. So we have some mathematical problem that we need computer to solve them. And the way the complexity of the algorithm and let's say the time it will take for algorithm to be run on computer is to look at the number of operations you need to solve a problem as a function of the size of the problem you want to solve. So right now, what I say is not specific to quantum, it's just algorithmic complexity. But basically, let's take a concrete example. Imagine that you want to factor a big number into prime numbers. So if you were able to do this, you could crack a money encryption system used to protect your data in bank transaction and so on. So the larger the number you want to factor, the harder it will be for your computer to find the prime number, which allow you then to decipher the message. But the thing is that on classical computer, for instance, solving this problem, with the size of the number you want to factor, so actually it's the logarithmic of the number of bits in the number you want to factor, but this is a technical detail. But let's say that when you increase the size of the problem, you will need an exponential number of operations as a function of the size of the problem you want to solve, so that your classical computer is able to solve that task. We know algorithms that run on quantum computer for which the number of operations is a polynomial. And for instance, Shor's algorithm is in this category to crack, to factor a prime number. So this is what we call an exponential speedup, is where the number of operations on a quantum computer, you have exponentially less operation if you want on a quantum computer compared to a classical computer. And when you realize that, it's obvious that at some point you will gain energy with a quantum computer. Because if the problem is so huge that you have a huge difference in the number of operations between the classical and the quantum, for a very large problem, the quantum computer will give you an advantage. So this is obvious. But what is less obvious is when this transition occurs. Because it might be that for small problem, the quantum computer could help to save energy as well. So this is a real question. To first know if there is really a distinction, or if in actually a wide area quantum computer could save energy, even for tasks that run for which quantum computers are slower than classical, which might be in the small problem region. And also, so first, we need to understand this transition for that, if it exists. And also, why is it interesting to study this question? So there are two reasons. The first one is that if we want to have large quantum computer able to solve complicated problems inaccessible from classical computer, we need to understand how much energy it will consume, because it could be that because of the energy requirement, we will not able to build this computer. And we have example in the work I present here, we'll talk after, where clearly you can have significant amount of power consumption or energy consumption to solve some problem. So we need to precisely identify that and to minimize the consumption of the computer and to think about this now so that we are not stuck in the scalability. There is another reason why it's interesting to think about this question, that it could be so that for small problem, maybe the quantum computer will not be significantly much faster than the classical one. Maybe it will even be slower than the classical one while you're closer to this region. But still, the quantum computer will save you energy. And it could give another motivation to build quantum computer, which is not computational, but energy one. So in this work, we provide a methodology that first allows to find where this crossing occurs, where the quantum give an advantage to the classical one. But more importantly, we are able to push this boundary to the left so that the energy advantage occurs the earliest. And it will also naturally increase the scalability potential of the computer. So the work presented here is basically a multidisciplinary holistic methodology that allows to minimize the amount of resource you need for quantum computer. So we apply it to energy and power, but it could be applied for other resources. So we will see the principle after, but basically it allows people working in algorithm, error correction, designing qubits, and also cryogenic and classical electronics to sit around the table and have a clear equation to solve, that they will all work together with a complete model of quantum computer, and they can minimize the energy requirement for the computer. And in this talk, we will apply this methodology in an idealistic model, but of a complete superconducting qubit quantum computer. So what I mean by idealistic, clearly, this is the value I will give will not be like the future quantum computer will consume this amount of power, because it's a specific architecture, it's based on optimistic assumption, but it's a proof of concept that you can optimize a full computer to reach that goal. And in practice, we will study how much energy and power is required to crack RSA on this specific model of quantum computer. And we will see the kind of order of magnitude that could be expected. Okay, so let's directly talk about the approach. So the methodology we use is called MNR, for metric noise resource. So let me explain the principle. So you have this concept presented on this slide here. So basically, we have what we call the metric. It is a number that quantifies how accurate your computer is. So as you might know, quantum computers are very fragile in the sense that the noise corrupts very easily the information. And so what you want is to be able to implement an algorithm with a success that is high enough. For instance, you want the success of your algorithm to be 90%. Then if you don't have the good answer, you rerun your algorithm a few times and you get the good one. But you want a high accuracy. So this is the metric part. It's a number that quantifies how good your computation is, and you could take the fidelity of the output state or basically the success of your algorithm. You have another element, which is the noise. So your quantum hardware is noisy. So you need to understand how the noise affects the quality of your operation. And the more noisy it will be, the worse your metric will be, the less the success of your computation will be. And you have the resource, the thing you want to minimize, which will be the energy and the power in this talk. And you want to minimize it. And basically you have control parameter in the middle. So we'll give concrete example after, but by tuning this parameter, you can modify how the noise acts on your quantum hardware, and at the same time, how much energy is spent in your computation. And basically, if you understand the connection between all those things, you can finely tune your parameter such that you have a high enough success while spending the least amount of resource. And so it requires an understanding of this connection. So the principle is very simple. It's a minimization of the constraint. Let me take a concrete example. Imagine that you work with superconducting qubits. So as you might know, they need to be at very low temperature so that they are not too prone to errors. And basically, when you put them at very cold temperature, it will cost you more energy to remove the heat produced at this low temperature. So if you think in terms of Carnot efficiency, it's very hard to remove heat at low temperature. It's the second law of thermodynamics. So it costs you a lot of energy. But it's good to put your qubit cold because then they are less prone to error. You have less noise. And so on one hand, it's bad to put the qubit at low temperature because you spend more energy. But on the other hand, it's good because you have a high success because you mitigate the noise. So you have higher success. But if you understand the connection here, basically, what you can ask is, what is the optimal qubit temperature such that my algorithm succeeds, so it works with a high enough rate. You can never have a perfect success, but with 90% probability if you want, while spending the least amount of energy. And then you find this non-trivial temperature. So the principle is very simple, but what is interesting is that you can use this simple principle in a complete model of quantum computer. So first, I will discuss a pedagogic example, single qubit gate, very idealistic, but just to see in more detail how we can do this. And then I will go to a complete model of quantum computer. And on the bottom right, you will see all the steps in the modeling so that we understand really how we can do this. So we will try to minimize the power to do just a single qubit gate on superconducting qubits. So a very simple example. And how do you drive qubits? So here you have your qubit here. It's inside a cryogenic unit. And to drive it, you send a microwave signal. They will interact with your qubit and you will do the operation you want to do. And so these qubits are at a typically cold temperature, TQB, so T qubit. You have also so the signal you send here go in a driving line, microwave cable. And basically, you need another component that experimentally put, which is an attenuator. An attenuator is basically a resistor, a big resistance. This will dissipate most of the signal that arrives. So it looks weird. Why do we dissipate signal? Because then it produces heat that needs to be removed by cryogenic. And so it costs energy to do this. The reason is that if you did not put this attenuator here, your signal will be produced at room temperature. So you will have a lot of noise. And in some sense, it will be as if your qubits were not at low temperature because all the noise occurring in your lab will directly be transmitted to your qubit. By putting this attenuator, yes, you dissipate a lot of signal, but it allows you also to remove the noise produced at room temperature so that you isolate nicely your signal, your qubit from the noise coming at room temperature, but you still have the noise occurring at your qubit. So here, the control parameter we'll choose will be the attenuation. We will optimize this, the level of attenuation. The more we attenuate, the more we dissipate heat, but the more we isolate the qubit from the noise, and the temperature of the qubits. So the colder they are, the more we spend power to keep them cool, but the less noise they will feel. And the formula here for the power, so that's the first part of the problem, is this one. And so again, we will optimize this A and T qubit. For now, they are variable. And this is the Carnot efficiency, and we multiply by the heat that has to be evacuated. This is the power to run our gate. So now we need to go to the noise. So as I said, the thermal noise, the temperature and the attenuation will play a role in the noise felt by the qubits. So for this, now we do quantum physics. We look at the equation of motion of our qubits, and it has a part where it's the perfect evolution called Hamiltonian. So here it's basically if you did not have noise, your equation will only be composed of that term. But because you have noise, you have an additional contribution here, which represents the thermal noise. And this contribution, you have different parameters. So let's just look at this in gamma and n noise. These are operator, but basically, if gamma is equal to 0 and n noise is equal to 0, you have no noise. Your evolution is perfect. But let's focus, for instance, on n noise. So this represents the quantity of noisy photon that reach your qubit. You realize that if you do not have this noise, for instance, you kill this term here. So your operation is less noisy if n noise is equal to 0. But you still have this part in the evolution. So it means that even if your qubit was exactly at 0 temperature and you attenuate of an infinite value, you will still have a noisy evolution. There is a fundamental reason for that. This is called spontaneous emission. So you can never, only by tuning the qubit temperature and the attenuation, make a qubit perfect. There is still other constraint that it's still noisy. And this is characterized by this spontaneous emission rate. And it will give you the quality of your qubit if in an ideal world, it was exactly at 0 temperature, at 0 Kelvin. And so now we need to understand how this dynamics is related to the parameter we want to optimize, the attenuation, the temperature of the qubit. So in that case, the number of noisy photon, the thermal noise, is related, as I said, to the attenuation temperature of the qubit. And to put it simply, so it's the same as I said before, but if the qubit temperature is 0, this thing is equal to 0. And if the attenuation is infinite, this thing is equal to 0. So for 0 temperature, infinite attenuation, we don't have noise. But this is how the noise is connected to the parameter we want to optimize. And now we go to the last step of the modeling, the metric, which quantifies how accurate the computation is. So here we took the fidelity of this gate, the worst case fidelity. And it also depends on the parameter we want to optimize. The colder the qubit are, the better the quality of the gate is. So now at this step, we have all the steps in the modeling. The resource is expressed as a function of the parameter we want to optimize, the noise and the metric. We are ready to find the minimum amount of power we need to successfully run the gate. And for that, before doing this minimization, we can look at the upper right plot here. So what it represents is the power consumption in color. The color represents the power consumption. The lighter it is, the more power it costs you. And it's represented as a function of the attenuation. So the more we attenuate, so it's expressed in this unit, the dB, but it doesn't matter for what I want to say. Just look that the more we attenuate, the lighter it is, meaning that the more power we consume. In the same line of thought, the colder the qubit are, the more the power we consume. So here, this is the high power region, and here, this is the low power region. But if you ask yourself, what is the success of my algorithm? How accurate my quantum algorithm is? Basically, you have the same behavior. You would like to be here such that your metric is high, meaning your gate is successful, high fidelity. And you would like to, and you don't want to be here because here your gate would be very bad. So you have this tension. It's not possible at the same time to ask for a good quality for your gate and a low power. You have a trade-off. If the higher you want your gate to have a high quality, the more power you will have to consume. And if you want a perfect gate, your power will be infinite because you will need your qubit to be exactly at 0 temperature. The Carnot efficiency diverge, and it's infinite in power, in energy, in whatever you want. So you have really to understand this trade-off. And when you understand this trade-off, what you can ask is, I want, for instance, this quality for my gate. So this gives me a fidelity I should reach for my gate. It gives you a constraint of how the attenuation and qubit temperature should be. And by looking at the minimum power along that line, so here you have this amount of fidelity. So the gate is successful 99.95% of the time, if you want to say it simply. And basically, when you look around that line, you can find the minimum power, it's reached here. And so you find the minimum power to run this gate with this success for your gates. And it gives you also the optimal qubit temperature and the optimal attenuation. So you find the minimum power, but also the way to reach it. So of course, this is a simple example here, just to put the concept. The method, as I said, is not very complicated, it's simple. But what is interesting is to apply it in a complete model of computer, to optimize the algorithm, the temperature, the number of the error correction you are doing. So this is now what we did, and this is now what I will explain. So the model we use is a complete model of quantum computer based on optimistic parameter, which for this reason, it's a proof of concept. So everything you see in this thing here is inside a cryogenic unit. Basically, each stage you see is a cryogenic stage. You have a stage at this temperature, this temperature, this temperature. And you see you have the cable and so on. So basically what happens is that you also have a lab, computer in the lab. But let's say, to put it simply, when you generate signals, they go down this line. You have the attenuator that we saw before. They interact with your qubit, you do the operation. And when you want to read the qubit, for instance, because we'll do error correction, you have signals that go up, they are amplified by amplifier, they are digitized, and then you have an algorithm that tells you which operation to do to correct which error. So basically, this is a full model of quantum computer, if you want, with additional component at room temperature that is not represented here. So the first part is here, all that generates signal. And it's at the given stage. That's the first parameter we'll optimize. We'll optimize the temperature of that stage. So the driving line, we will optimize the temperature of each stage here under attenuation. The amplifier, we don't optimize that temperature. And the qubit, we optimize the temperature of the qubit and the attenuation. And we will also do quantum error correction. So we'll have a number of physical qubits per logical qubit. And so this is what I will explain now. This is also a parameter in our problem. Okay, so not everyone might be familiar with error correction, so I will try to explain simply how it works. So as you know, so the noise is really the problem in quantum computing. It's hard to have high quality answer. There is a strategy that you can do, which is that if the quality of your qubit is high enough, you can protect them by error correction. And the point is the following: you have a parameter. So here we use a specific class of code, which are called concatenated. But the overall principle works for any code. It's just we had to take one code. I will explain why we took this code after. So when you want to do an algorithm, what do? You look at your favorite paper that describes you our Shor algorithm. This is the circuit, and you need a given number of logical qubits. The number of qubits given by this algorithm is the number if the qubits were perfect, but the qubits are noisy. And so a strategy is to encode this logical qubit, the qubit needed by algorithm, by a given number of physical qubits. With this code, we have 91 to the power k physical qubit per logical qubit, where k is a parameter that we will optimize. So you see that the greater k is, the more physical per logical qubit we have. But why do we want to increase the number of physical per logical qubit? This is explained by the second line. Each gate protected by error correction is called a logical gate. And basically, what you do is that you have a constant here called the threshold. And here you have eta, which is called the physical error probability. So it's the probability of error of your gate if you did not do error correction, if you directly did your gate at the physical gate, not protected. You see that if eta is lower than the threshold, here you have a number that is less than 1. And it is at the power 2 to the k, meaning that when you increase k, this thing decreases, and the probability of error of your logical gate gets smaller and smaller and smaller when you increase k, if you're below the threshold. And so basically, you see that when you increase k, you have a larger computer, you have more qubits, so it costs you more energy, but each gate is more accurate. And because of that, you can run a longer algorithm, because the longer the algorithm is, the more each gate in the algorithm should be accurate, so that you have a trustable answer at the end. And so this is how it works, and this is the code that we use for that. And we also access the number of operations per unit time per physical qubit, because this is the logical level, but it's done by the error correction construction, basically. And we can access all that. So one comment, here we choose this code, still code concatenated. Experts in error correction will not like to use this code to scale up. They would like to use more, let's say, a state-of-the-art code, which is like, for instance, a surface code. The reason we use that code is because we wanted to have a complete model of quantum computer where everything is modeled. With the surface code, there is still an open question to know how much energy will be required to analyze let's say, to diagnose which error is occurring on the physical level to correct it. Basically, you need classical algorithm around error correction to tell you, oh, this qubit had an error, so then I need to do this operation to correct it. And because of that, because this is a black box, the energy estimation of that, we did not want to go in that way. We prefer to have a work based on maybe not a state-of-the-art code, but where everything is modeled. But this is why also it's a proof of concept, what I say, not the estimation you will have if you build a quantum computer in practice. Okay, so at this point, basically, here, the resource is specified, it's the power consumption, all these things, and the control parameter I will optimize, all the temperature, the number of physical qubit per logical qubit through the parameter k, and the attenuation level are specified. And so now we can move to the next part, the noise. I won't go into detail. It's the same noise model as before. The temperature corrupt the qubits. We have spontaneous emission, same noise model. And finally, there is the metric. So now that we do error correction, we will use the probability of error of a logical gate given by error correction. So the way it's used is very simple. You have a given number of logical gates in your algorithm. Each gate has a probability to fail, which depends on all the parameters we want to optimize. So it's a function right now. It's not a value, this thing, it's a function. And we ask that along the computation, the probability that no gate fail along the computation, so that the algorithm give a bound on the success of the algorithm. And then we ask, okay, we want our algorithm to be successful, let's say 2/3 of the time, which gives us the constraint we need on this parameter here. And yeah, that's what we took. And now we can look at the results. Yeah, okay, so I already said it. It's mostly a proof of concept, but it can still give us a very good idea of what is likely to cost a lot in a computer and what happens if you do not optimize the build. Because even if it's a specific architecture based on optimistic assumption, it's still a complete model, and we can already have intuition on the energy costs required by large-scale quantum computers. So the main assumption we are doing, they are summarized here. The lifetime for our qubit is very good. It's 2 orders of magnitude better than, between 1 and 2 orders of magnitude better than the state of the art. We have no choice if we want to do error correction. And also because we use the code we use, it has a poor threshold, meaning that the qubit should be very good in order to make error correction useful. As I said, there is electronics in the computer. Here we took an order improvement on the state of the art in CMOS electronics. But after discussion with experts in that field, basically it's a reasonable assumption to make because there are optimization that can be done by this community, And for the efficiency of the full cryogenics, we took the best efficiency that you could hope for, which is Carnot efficiency. So it might look as a very optimistic assumption, but actually it's not. If you think about the Large Hadron Collider in Geneva, where they do particle physics, it works at the fraction of Carnot efficiency. So if you want to aim for large-scale quantum computer, they might consume significant amount of energy. You should ask your cryogenic expert to reach Carnot efficiency, and they know how to do it because they already did it. Okay, we are almost ready for showing the results of the consumption for algorithms. So just the algorithm will be summarized by a number of logical qubits we need and the number of time steps, so the number of sequence of gates we need for this algorithm. And this is what we can see here on this plot. So what this plot shows is, as a function of the number of logical qubits and the number of time steps in the algorithm, the power consumed by our algorithm, and in terms of duration, it will depend on the algorithm, but I will comment on this after, to run a given algorithm. So here, you have RSA 2000, is the current encryption protocol used by banking system and so on. If you use Shor's algorithm, in our specific model, assuming qubit as good as we have, it will cost 7 megawatts for a few hours. So it's comparable basically to the power consumption of a supercomputer for a few hours. We can look at the power consumption for different problem size that are shown here. And what you see here is that the power brutally changes here. So these brutal changes that you see here are the moment we need to add physical qubit per logical qubit. So we are doing more error correction by going from here to here. And the script tells us exactly when we should add physical qubit per logical qubit, such that we are successful, but while spending the least amount of power. One thing that you see is that the longer the computation you do, the more power it costs. So this is not so obvious. So it depends on who you talk to, but in some sense, it's not completely obvious. If you imagine you want to run your computer, that you run it for 1 hour or 10 hours, the energy per unit time it consumes, so the power is the same. Of course, it will consume more energy because you ask it to run for a longer time, but the power will not significantly vary. In quantum computer, because they are so sensitive to the noise, the longer the computation you are doing, the more you have to protect your qubit. And so it brings you an additional energy consumption. And this is why the power consumption increases with the duration of the algorithm. So as I said before, this work is not an estimation, but an optimization. So we need to understand what is happening. We have the physics of the computer. Let's understand it. So on the right, if you understand this, you understand everything, basically. So here, we start here. That's the optimal temperature for our qubits. We are just after this transition, meaning that here we have more physical qubit per logical qubit than here. So we did more error correction. Because we are doing more error correction, what the script tells us is that there is no need to maintain your qubits super cold. You should put them at a high temperature. You would save energy by doing this. Don't maintain them at cold temperature because you do a lot of error correction. So your code allows you to resist against the bad quality of your hardware. So you put them at a higher temperature, you save energy, and then you increase, for instance, the duration of the algorithm you want to implement. You add step in your algorithm. And now the temperature of the qubit has to decrease until you reach that point. Here the qubits are at 4 millikelvin, so they are very cold. And at this moment, the script tells you, if you want to run a longer algorithm, you should exactly at this moment add physical qubit per logical qubit. And then when you will do this, you could increase the temperature of your qubit. No need to maintain cold because you will do more error correction, so increase their temperature. And basically, yeah, this is what is happening, and you should do in the script tells you should really do the transition here and not here. If you added physical qubit per logical qubit here, you will spend more energy than what is necessary. So this really tells you exactly when you have to do it. So this effect is really multidisciplinary and holistic because it's intrinsically relating the physics of the superconducting qubits. As you see, the temperature are quite cold, 500 millikelvin. It's close to the absolute zero. And this is because we work with superconducting qubits. And at each point, at each algorithm we are doing, we optimize the complete quantum computer, and in particular, its temperature. So the way we implement the algorithm has a role in the optimal parameter we find. Of course, the choice of error correction code we do plays a role. It indicates us the transition we are seeing here. And of course, the model we use, the fact we have cable, all these practical things from the engineering side, cable, electronics plays a role in the bill as well. So what we see here is a holistic phenomenon that will occur for any kind of quantum computer. The value will differ for sure, but the physics I'm explaining will occur for any kind of model. So far, basically, I hope we understand the principle. You need to connect the success of your algorithm to the resource it costs to you. The approach is holistic, and we can optimize a full computing architecture. So now I will discuss a few last things. So the first one is to compare the energy efficiency of quantum and classical computer. So I will first tell you how not to do the comparison because it's instructive to understand how quantum computer will use energy. What you could do is to look at an algorithm. You have a number of operations it uses, and you know the energy per operation. For instance, in a classical computer, the energy per floating point operation, so let's say the fundamental operation, if you want in a classical computer, is 10 to the power minus 12 joules. So you multiply this by the number of operations, it gives you an energy cost for a full algorithm. You could think doing the same on a quantum computer. But if you do it, you will either have an algorithm that does not work, it doesn't give you the success you want, it will give you a bad answer, that consume too much energy. So let me illustrate it. And it's the same explanation I said before, but presented in a different angle so that we really understand what happens. Imagine you have a quantum algorithm when the only thing you have to do is a single one gate. If you and you want a success that is 90% for your algorithm. If you just have one gate, you do not need to do error correction. Having a gate that provides you an accuracy that is 90%, this kind of fidelity can easily be achieved by experimentalists. You might not even need to put them at super cold temperature. You could increase a bit the temperature because 90% fidelity, it's not so big. So then your energy for this unique gate will be very low. But now imagine that you want to do the same gates, but an algorithm composed of this gate, but run a billion times in sequence. You still have, let's say, 1 qubit or 2 qubit. Here it's a synod, but let's say, okay, 1 qubit, 1 gate. And now you have a billion gate in sequence. And you want your algorithm to be 90% successful because otherwise you cannot say anything about your data. Because you want this billion gate to give you a success that is 90%, each individual gate should be super accurate. You cannot do a sequence of billion gates that each of them have 90% accuracy because at the end you will not have a 90% accuracy. You will have a very low accuracy. Each of your gates should be very accurate to ensure this success. So it means that the energy required per gate will be much higher in this algorithm than in an algorithm composed of a unique gate. If you do not have this dependence, either it means your algorithm will not work, you will spend the same amount of energy for 1 gate algorithm or 1,000 gates, and meaning that your success will be bad because you will not have enough energy per gate to have a high success. Either you just spend too much energy. Either maybe your algorithm will be good if you do not acknowledge this dependence, but you just spend way too much energy to do each individual gate. So an energy efficient computer, quantum computer, the energy you do per gate depends on the algorithm you want to do. And you need to have that to have an algorithm that is successful and is energy efficient. So then what you can do to have an energy efficient quantum computer is to do the same kind of thing we did before. You just take the full problem you want to solve and you apply the optimization I said before, but really on the full algorithm. And you ask, which of the classical or quantum computer spend the least amount of energy to solve the problem? And we play that role to see breaking the RSA encryption for various key size. So on the classical side, in our model, there is called the general number field sieve algorithm. That's the best known classical algorithm able to solve that task. Of course, you could not break RSA for size of key that are currently used in banking system. Otherwise, it will not be safe. But you can use it for smaller key. For instance, for 830, this is the key size that JNFS could have broken this key on a classical supercomputer. So the current encryption is RSA 2000, to give you an idea. And then from this, we can extrapolate the energy and time it will cost if someone wanted to run this classical algorithm, JNFS, to break RSA. And on the quantum side, we consider Shor's algorithm that we already briefly discussed that before. And now you can look at this curve. So this curve here in the x-axis, it is the size of the key you want to break. And in the y-axis, it is the time in second it costs you. The black line is the time the classical computer will take. So you see that it quickly increases with the size of the key. This is normal because the classical computer has an exponential cost in the problem size. And here we have different models of quantum computer represented by different colors. So I won't comment all the colors, just look at the green one here. So when these lines here are below the black one, it means the quantum computer is faster. And here the quantum computer is slower. And below you have what is called the energy efficiency. So basically we can access the energy cost, but what matters, I won't enter in the detail what it represents. If the green curve is higher than the black one, it means that the quantum computer spends less energy to solve the task. And if you are here, the quantum computer spends more energy to solve the task. And here we have an example where the quantum computer is slower than the classical one, but spend less energy to solve the task. So this is based on, at the same time, very optimistic and very pessimistic parameters. So this is why, again, it's a proof of concept that I'm saying here. That is just to say that we can precisely assess this region. And this is a region that should be investigated, a quantum energy advantage without a computational one, because we can precisely understand this transition. So maybe we could design a small quantum computer that could be more energy efficient than classical computer without providing computational advantage. And maybe it could be a new motivation to build quantum computer because it might be easier to reach than the computational advantage because the computer doesn't have to be so big. And this is my last point before the conclusion. So what I presented is an optimization. Natural question is, what does it bring? How much energy can you save if you optimize or if you did not optimize? So in some case, you do not save much. In some case, okay, maybe you would save a factor of 2 in the energy or power consumption, but not that much more. In some case, the gain can be huge. And we have example where if we did not optimize, the quantum computer to solve some task could spend 10 gigawatts, which is 10 nuclear reactors, without optimizing. But with optimizing, with applying this methodology I present, we can bow down to 2 megawatts. And so the duration of the computation is the same in these two examples. So that the energy is just 10 gigawatt multiplied by a few hours and 2 megawatt multiplied by a few hours if you wanted to have an energy consumption. So in some case, I'm not saying it's always the case, but in some reasonable case, you can have huge gain compared to if you did not optimize. And there are basically, there is, I'm sorry, so there are one question. There are examples where the strategies used to save energy, you cannot guess it by simple estimates. So to give an example, there are cases where it's better to do more error correction, to have more physical qubit per logical qubits, so a bigger computer, Why? It's more energy efficient because it allows your qubit to work at a higher temperature. And at the end of the day, you save energy. This kind of thing is not possible to understand if you do not have a full model of your quantum computer. But this is what we observe, and we think it's interesting. Okay, I will skip that point. It's not so important. So now, so that's it. I will basically conclude here. So this is really what matters, this approach. The key point is each element you put in the computer, it consumes energy, but it changes the success of your algorithm. If you understand the two aspects, you can ask to minimize the energy while having a successful computation. And then you can optimize many things. And so this is the interesting aspect. There are clear interdependencies. Having a more physical qubit per logical qubit can be more energy efficient. Having a bigger computer can be more energy efficient than a small one sometimes because of this surprising strategy with the temperature. Computational energy advantage might occur in very different regime, which could be a motivation to study in itself to see if we can find energy advantage. And finally, overall, this kind of approach can also make prediction, help the design of quantum computer, because we could perhaps use that to make roadmaps to see, okay, if my qubit have this quality, if my electronics consume that much, this is the energy that will be consumed by my computer. And then it can help to make this kind of multidisciplinary roadmaps. So most of what I presented today is based on this preprint, which is based on this thesis, on my thesis. This is a preliminary related work. And the work presented is also the seed behind an international initiative that has been launched called the Quantum Energy Initiative with this website. So its goal is to federate the community to make energy efficient quantum technologies. And many partners have signed this initiative, for instance, Microsoft and many quantum startups, Pascal, Candela, and so on. And so these kind of questions are also currently discussed as a IEEE work group, which aims to propose new international standard on energy efficient quantum computation. And so feel free to join. So this work and other work are discussed to see if we can make new standards at the international level to make energy efficient quantum technologies. So thanks. So to recall, this work has been done in collaboration with everyone here. So everyone participated in this work. So just to comment a bit, so Jin Hao was a postdoc in the Center for Quantum Technologies at Singapore, supervised by Hui Kun. So they are specialized in fault-tolerant quantum computing, so quantum computer with error correction. Yvan Tonard is a researcher in classical electronics at the CEA in Grenoble in France, where I did my PhD. And Robert Whitney and Alexia Ofev are researchers in quantum thermodynamics, also at Grenoble. They were my PhD advisor, and now Alexia Ofev is working in Singapore, the Center for Quantum Technology. I just thank for all these persons here that greatly helped to improve the paper, in particular Olivier Ezrati, who is consultant in quantum technologies, and helped give us very good advice to make the model better, more realistic. And so, yeah, this is my current affiliation, and I will be a Marie Curie Fellow in the same lab in September. So thank you for your attention.
Hey, great. Thank you. Thank you, Marco, for this great presentation. Very interesting indeed. Let's see if we have some questions. I don't see any questions on the chat now, but maybe someone would like to unmute and ask. If not, you can also post your question on the chat and we'll ask. But anyway, I can start. So yeah, you said about this dependency of energy consumption on the qubits, but is there any dependence on the type of a quantum gate? I mean, is the energy consumption the same for, let's say, Hadamard's gate and X-Pauli gate, for example, or are there differences? I would expect that there might be a similar level.
Yeah, so that's a very good question, actually. So in general, everything can depend on everything. So now in practice, I guess it depends on the following. So it depends on the way you want to do your gates. So let me do an example. if you want to do a rotation around X or around Y, or this is the same kind of interaction that occur at it's typically microwave interaction with your qubits, superconducting qubits in this example. So they will roughly consume the same amounts of energy. But you have different gates you can do. For instance, for some, you might want to tune the frequency of your qubit because it can allow you to do a rotation around the z-axis, for instance. And this is a different kind of interaction that occurs. You need, for instance, to inject magnetic field to do that. So because it's a different interaction, it will have a different energy cost. And to finalize on this comment, there is also the fact that, as I said, there are two things. You need to understand the power in itself to do the gates, but also how noisy the gate is. Because the more noisy it is, the more you will have to cool down your qubit. And it's an indirect contribution to the energy cost. And so, for instance, a CNOT will typically be more noisy than a single qubit gate. So even if the signal you have to send has low intensity, maybe lower intensity than a single qubit gate, maybe it will ask you to actually lower the qubit temperature if you want to do this CNOT, more than if you had to do a single qubit gate. So yeah, I don't know if it answers the question, but you have a lot of different things.
Yeah, that's what we could expect. All right, and what's the dependence on the type of the technology used to build a quantum computer? For example, you said about superconducting, but how it would work for ion traps, for example, or photonic quantum computers?
So indeed, all the figure could drastically differ depending on the platform. Everyone has to do his homework and realize what it costs in its architecture. But to say simply, in ion trap, superconducting qubits, the cryogenics might play a significant role in the bill. If you think about photonic qubits, you need a little bit of cryogenics, but it's not, it's very light compared to. So that's, I would say, a significant difference in the energy requirement. But I will also say that there is, actually, we are very surprised in that work that the cost of the cryogenics might not dominate even for superconducting qubits. Because all these electronics that generate the signal, that detect error from error correction, might be we found in many cases that it's optimal to put them at room temperature, and it can completely dominate the cost in some cases. So I'm not saying cryogenic will not dominate, I'm saying it's an open question. And this is surprising, because when you discuss with people, they will directly say, oh, cryogenic will dominate everything. And for me, it's not so clear. So yeah, that's a comment on that.
Great, fantastic. I see that there is a question on our chat from Surajit. Is there any comparison on what Q-gate, I believe it's quantum gate, consume more or less power?
Okay, so yeah, I think that's related to the question you asked earlier.
Yes.
So yeah, this is what basically, the same answer. You have to understand the noise and the power consumption of the gate. Yeah.
Okay, good. Yes, thanks. All right. Do we have more questions from our participants? Okay, I don't see more questions now. So, Marco, thank you once again for this very interesting presentation, answering your questions. Let me maybe just share the slides, my slides once again. Yes. All right. I hope you can see my slides again. Yeah, I just wanted to say that this was the last episode of Warsaw Quantum Computing Group in this academic year. We'll come back in October, but there will be just a summer break for holidays. Of course, we would like to thank once again our strategic partners, Cogs, Narto, and Sonovero R&D for supporting us, as well as thank to our honorary partners. And if you are interested in our meetups, let's stay in touch. Feel free to join our mailing list, join our Facebook group, follow our fan page or YouTube channel, or profiles on Twitter and LinkedIn. So we hope to see you next time in October, most likely in October. There are some chances that we'll decide to organize a special episode during the holidays, but most likely we'll come back in October. Let me see if there are some questions. There's a question about sharing the PowerPoint slides. Marco, would you like to share the slides?
Yeah, I can share the slide, but it will also be uploaded on YouTube, right? the talk?
So yeah, the video will be available on YouTube, but
Okay.
I can also upload the slides to the
Okay, I can share
website.
the, yeah, I
Yes,
will send you
you
the
can put it
slide.
on the website. Okay, great.
Okay.
So you can send it to me by email,
Yeah.
and I will upload it to the website. Okay, great.
Okay. Thank you.
Thanks. Thank you, Marco. Thanks everyone for joining.
Bye.
See you next time. Bye bye. Cheers.